Hi guys, today we'll be starting our discussion about threads. In previous videos, we saw how we can create new processes using fork and use exec to run a new program in the child process. We have also seen how to monitor child processes using wait system call, otherwise we'll be creating zombies on our system. Let's understand how threads differ from processes, then we can dive deep into what threads actually are. Let's see a few basic differences between a process and a thread. Process offers concurrency and isolation. By concurrency, I mean there can be two separate tasks being performed in two different processes, but both of these processes are isolated from each other. Each of them have their own memory footprint and they execute independently of each other, whereas threads only offer concurrency and not isolation. Two threads can execute two tasks parallelly, but both of these threads would be running inside the same process and they don't offer isolation. One thread can step into the memory of another thread and can do some reading or writing in that memory region. That is why we say isolation is not offered when we talk about threads. Sharing data between processes would need us to perform inter-process communication by using any of the IPC mechanism offered by the OS. It could be a shared memory segment, a message queue, a pipe, or a socket. Whereas in threads, it is easy to share data. Since two threads running in the same process are not isolated from each other, data can be shared between two threads quite easily, and it is as simple as writing something onto the shared segment. I'll explain the idea of sharing data in threads better in the next slide, where I'll show you the virtual address space of a process running multiple threads. Creation time of process is large as compared to creation time of threads. To create a new process, the entire memory of the running process has to be copied, whereas in case of threads, no duplication is required. Everything runs within the same process. The only thing that is required in case of threads is setting up a separate stack for the thread. This is the virtual memory address space of a process which is running four threads. The main program can be thought of as a main thread, and the main thread can be calling thread creation APIs to be able to create thread 1, thread 2, and thread 3. Each of them have their own separate stack sections. The stack for the main thread can also be seen. Although the location of the stack for each thread could differ, but this would be the basic idea where a thread creation would lead to setting up a stack. The text section contains the code for the main thread and the other three threads as well that got created inside the main thread. We'll see thread creation in more detail as we progress through the video. We also have to understand there are few attributes that all of the thread created inside the process will share. They will have the same process ID. They will have the same parent process ID, which I have indicated with PPID. They will be sharing the open file descriptors. Any signal handler that has been set up would also be shared. File system related information like umask, current working directory, and root directory would also be shared amongst all the threads. Umask is a process related attribute that dictates what all permissions would be turned off when a new process gets created. Would it have read, write, or execute permissions is dictated by umask. Everything that is set here in umask would be turned off by default when the new process gets created. All of these four attributes are process level attributes. That is why all the threads will be sharing these four properties. Few attributes that are not shared are thread ID, signal mask, and the most importantly, stack section. Thread ID is an identifier to be able to identify the thread. Signal mask is the mask that specifies what all signals are blocked in a particular thread. And as we have already seen, each thread would have its own stack section. The heap, data section, the text section, shared libraries, everything else is also shared. I have not explicitly added them under the shared attribute section, but all these memory regions are also shared amongst the thread. That is why when one thread has to communicate with other thread, it can simply write something onto the heap and other thread can go ahead and read that information. That is how data sharing can happen so easily between two threads. This is the thread create function, which is available in pthread.h library. As you can see, it is taking four arguments. For first is the thread object, which contains the thread ID and is used to identify a thread uniquely within a process. ATTR dictates any thread specific customization that we would want for the new thread that is getting created. For now, we'll pass ATTR as null, but inside ATTR, we can set stack size or signal mask to use thread properties other than the default properties. The third argument is the thread function. This is the function that gets kicked off whenever the thread is created. It always returns a void star and always takes void star as an argument. The fourth argument of pthread create API is the void star argument that is passed to the thread function. Pthread create API returns 0 on success and a positive number which can indicate the error condition if thread create API fails. We'll see an example program where we'll create two separate threads within a process and make them do two separate tasks parallelly. To understand the concept of threads, I'll write two print functions that have separate print strings inside them. For the sake of simplicity, I'll be calling them simple print 1 and simple print 2. Now let's try to run them. I have called simple print 1 and simple print 2 from the main function. Simple print 2 will never be printed. The program will always loop inside simple print 1 where it will be stuck inside a while loop and never move to simple print 2 function. We'll now run simple print 1 function inside a thread. Simple print 2 is still part of the main thread, whereas I have created a new thread for simple print 1. Pthread create API takes four arguments. First argument is the thread object. Second argument is the ATTR. We are relying on default attributes and passing null. Third argument is the thread start function. And fourth is the argument that has to be passed to the thread start function. We have to make sure simple print 1 follows the signature of a thread start function. which means simple print 1 will now return a void star and will take a void star pointer as an argument. I'll add a return null to this simple print 1 as a return value. I'll also add a sleep of 1 second inside both the print functions to prevent unlimited prints onto the console. We can now see both the print functions are alternating. Both of them seems to be executing parallelly. Let's also talk about a scenario where main thread finishes before the simple print 1 thread completes its task. For that, I am going to count in opposite direction in both the threads, but in simple print 1 thread, I have a count of 8 times, whereas in simple print 2, I have a count of just 5. Let's see what happens in this scenario. Simple print 2 on the last statement is saying I is 0, whereas simple print 1 has just reached the I value of 3. It skipped last few of its print. This is because simple print 2 didn't wait for simple print 1 to complete its task. For that we have a pthread join API which enforces a wait until the specified thread also completes its task. We'll ask pthread join to wait for T1, which is the simple print 1 function. With this, we'll be able to see both the thread running till completion. Even if main thread completes first, it will wait on pthread join until the other thread also completes, and then the program would exit. Pthread join can also be used to retrieve the return value of the thread. The second argument in pthread join is used to receive the copy of the terminated thread's return value. We'll talk about thread join in more detail in our upcoming videos. We'll also see why it is important to join a thread.